This is a lecture for Monday, April 6th. We will be completing our discussion of quantum chromodynamics. Today we'll be focusing mostly on lattice QCD simulations. So we've talked about this before. Lattice QCD simulations is where we imagine that space-time is divided up into a lattice. I've shown you here a three-dimensional lattice, but it's actually a space-time lattice, so you actually have a four-dimensional lattice for space and time. And what you do is, on each of the lattice grid points, you have the quark fields. For example, I have a quark field Q at this site R, and let's say this is the one direction, perhaps the x direction, and this is the two direction, perhaps the y direction. Then this is going to be the lattice site at R plus the lattice unit vector in the one direction. Okay, so this will be the quark at R, this will be the quark field at R plus the unit vector E1. Similarly, we have the quark field at R plus the unit vector E2. Now, what's a little bit unusual is that though the quarks sit on the lattice sites, the gluons actually are represented by these SU3 matrices. Okay? So this is how you put gauge fields on the lattice, in particular quantum chromodynamics. You actually work with the group elements on the links of the lattice, and this actually allows you to have an exact gauge symmetry where I can do a gauge transformation rotating the quark fields. Remember, you think of the quarks as some three-component column vector. I can make some sort of a rotation in that three-component color space here, but then I can make a different rotation for the quark fields here. But to compensate for that, this gauge, what's called the gauge link field, is an SU3 matrix which can cancel those rotations and give you then a gauge invariant combination. So that's the game, and this was the prescription that Ken Wilson, who came up with this way of putting gauge fields on the lattice. Okay, so we have this gauge link field U1 at the site R that gives this link in the one direction. Okay, and we also have then a link in the two direction that connects these two lattice points. Now, the way then that the lattice simulations work is you then use Monte Carlo simulations to make a bunch of configurations for these gauge link fields, and then that will correspond with, because they couple to the quark fields, you end up getting matrices out that you have to calculate the determinant of. And so there's lots of things like calculating determinants of matrices, as well as calculating inverses of these matrices, as you sample all possible SU3 gauge link fields for these fields here that I'm talking about. Okay, when you do that, you can get some, well, it's a very difficult calculation you have to put in on a supercomputer, but here are some results that we'll talk about now. So these here are some results for the low-lying hadron spectrum, in particular mesons and the baryons, by the BMW collaboration. If you're wondering, the BMW collaboration stands for Budapest, Marseille, and Wuppertal, the three institutions where the collaboration initially was founded. And they did a calculation where they essentially did all the single hadron particles. They calculated their masses, and you can see, okay, so the pi and the kaon, these were not predictions, but these masses were actually used to fix the quark masses used in the lattice QCD simulations. But once those were used, everything else is a prediction. And what's beautiful here is that, see these predictions in the red dots with the error bars, you can see they're in nice agreement with the experimental values. Okay, they're spot on. In the cases where the particles have a significant width to them, their resonances, the width is here, but these calculations do not try to predict the width. That's a more difficult calculation. The same BMW collaboration also made a few years later made a calculation of the splittings in the masses of different hadrons within a given isospin multiplet, like, for example, the neutron-proton mass difference. Okay, so that's here delta n, which is the neutron minus the neutron mass minus the proton mass. And we also have the splittings for the sigmas, sigma minus minus sigma plus, and the Xi, or the cascade particles, Xi minus minus Xi 0. And what you can see again is that the predictions are in good agreement with the experimental values. What's quite impressive is that in some cases, like here, the QCD error is actually small. Sorry, the lattice QCD predicted error is smaller than that of the experiment. And here there's not even any experimental data, and so this is a pure prediction. Now, what's interesting about this is that there's two effects that are sort of competing against each other in the difference between the neutron and proton masses. One is the fact that the down quark mass is larger than the up quark mass, and at the simplest level, the neutron is an up down down system, and the proton is an up up down system. So as a result, because the down quarks have a heavier mass, the neutron has a heavier mass. That's the so-called QCD contribution, and so the QCD part of the mass difference is about 2.52 MeV with these error bars from the calculation. Now, but there's also a difference between the neutron and the proton coming from the electromagnetic effects, the fact that the proton has a charge of +1 and the neutron has a charge of 0. So remember, the up quark has a charge of +2/3, and the down quark has a charge of -1/3, and so when we add these together, we have a +1 for the proton and 0 for the neutron. And because the proton has charge, there's some repulsion here. As a result, the mass that tends to make the proton mass a bit larger. It costs you some more energy, and so that's why the neutron minus proton masses from the quantum electrodynamics is -1.00. And so you get 2.52 minus 1.00 gives you about 1.51. And that's where you end up, and it's in good agreement with the experimental values. So you can see, so there's this interesting competition. People did not know how this difference was going to work, well, from first principles until these calculations were done. So this was quite beautiful. In fact, there's a statement to this effect by Frank Wilczek. We discussed Frank Wilczek. He was the Nobel Prize winner who was involved in asymptotic freedom, talking about how the quantum chromodynamics coupling was changing as a function of the energy scale. And so he says the neutron-proton mass difference, one of the most consequential parameters of physics, has now been calculated from fundamental theories. Okay, so he calls it revolutionary progress in nuclear physics. Now, there was also more recently, just a few years back, a calculation by the NPL-QCD collaboration. So NPL, NP stands for nuclear physics, L stands for lattice, and QCD is quantum chromodynamics. And so they did a calculation of a reaction, proton-proton fusion, the burning process in the sun that we talked about, the first step in hydrogen burning. And they did this calculation by putting two nucleons in a box, and they looked at the conversion from two protons to a deuteron. And they actually coupled some external weak interaction fields to be able to calculate this transition rate. Now, here's some calculations. Well, we'll talk first about the experimental status. The spin structure of the nucleon. So we have a nucleon. I told you, for example, for the proton, at the simplest level, it's up in a down quark. But in reality, there's a bunch of virtual particles all over the place, right? You have gluons. You have let's say an up and anti-up quark popping out of the vacuum. You may have strange anti-strange stuff in the vacuum. You have gluons all over the place. And so the question is where does the spin of the nucleon come from, the spin of the proton? And so you know that the nucleon has a total spin of 1/2. It's a spin 1/2 particle. You know that from the beginning. But who carries that? So there's sort of the simple picture that I've been telling you. The simplest picture is you just have it coming from the quarks themselves, but that's not really what goes on. You know it's much more complicated. Okay, so then maybe a slightly more complicated picture is that you have the quarks, you have then these, what are called C quarks, these virtual pairs of quarks popping out of the vacuum, quark-antiquark. And then maybe you have some gluons also that are polarized. But now, well, towards the future, we realize things are even more complicated than that. We have orbital motion, so we have orbital motion of these quarks, what are called the valence quarks, the original up-down quarks, as well as the C quarks, the ones that appear out of the vacuum as pairs. Okay, so they carry orbital angular momentum, as well as the gluons carrying orbital angular momentum. So it's a very complicated mess. And so then, how much is carried by each component? So there was recently, a few years ago, 2017, Lattice QCD calculation by the Kentucky group. Kei-Fei Liu was actually the senior scientist on this project, and he actually gave he gave a seminar on exactly this not too long ago at MSU. So we're talking about the spin of the gluons and the proton, and what they found from these lattice QCD simulations is that about 50% of the proton spin comes from the spin of the gluons that bind its quark constituents. So that was kind of surprising that so much was actually coming from the gluons. Okay, now let me talk a little bit about the spectroscopy, the sorts of states that you see in experiments and the comparison with lattice QCD simulations. Okay, so it turns out that there's only certain types of we're going to focus for the moment on mesons. So remember, mesons are the states that look like QQ bar. Okay? And so what's going on here is that there's some intrinsic spin, total intrinsic spin, that can be 0 or 1 because the quark has spin 1/2 and the antiquark has spin 1/2. And so these can be added together to give 0 or 1. Okay? Now, then the angular momentum then can be 0, 1, 2, and so on. Okay? Now, if you're taking this quark picture, this simple, just what are called valence quark picture, these are called valence quarks because it's this is the simplest description of what's going on in these mesons. We're not talking about C quarks, we're not talking about gluons, we're just talking about these valence quark and antiquarks. So if I think of these in a very simple non-relativistic model with having the spin and the orbital angular momentum, then I can predict what the parity will be. So the parity is going to be, there's going to be a factor of -1 coming from the fact that the quark and the antiquark actually end up having opposite intrinsic parities just from the get-go. But then if we have a orbital angular momentum L, then there's another factor of -1 to the Lth power coming from just the fact that whether you have an S wave or a P wave or a D wave, you get them because of the parity properties of this orbital motion, right? Either it's even under parity or odd under parity for the different angular momentum states. So the parity is going to be L plus 1 -1 to the L plus 1. Now, under charge conjugation, we didn't really talk about this very much, but it's simply, this is given by the overall symmetry of the spin and the orbital angular momentum wave function. So it turns out there's a factor of -1 to the L times -1 to the S. So that's -1 to L plus S. So now what you can do is, if this is the way that mesons are built up, if this so-called quark model picture works, then you can make a table. You can say, all right, let's say let's take different values for my S, L and my S, and we can determine what the total spin can be, and the parity and the charge conjugation quantum numbers. Okay. Now these J must obviously, that's just adding orbital and the orbital and the intrinsic spin angular momentum together. We know how that works. Okay, we don't have to explain that. So let's start from the beginning. Suppose I have L equals 0 and S equals to 0. Okay, so if I add L with S together, what angular momentum can I get by adding 0 with 0? The only thing I can get is 0. All right, now then the parity that I can get would be minus 1 to the power 0 plus 1, so that would be a minus. Okay, minus 1 to the power 1 is minus. And then the charge conjugation is minus 1 to the power 0 plus 0, that would be just plus. Okay, now let's go on. So I can have, let's say, L equals 0, and I can spin 1. And now in this case, I can have spin J can equal 1, all right? And then, adding angular momentum 0 with angular momentum 1, I can get angular momentum 1. That's the only thing I can get. And so now in this case, the parity will end up being, again, here, minus 1 to the L plus 1, L equals 0, so I get minus. And then S here is 1 and L equals 0, so I get minus. So there's a prediction here that in the quark model, we can see a 0 minus plus and a 1 minus plus for these so-called JPC values, and then we can continue on with the higher angular momentum. And so that's what's exhibited here. These are the states that you get in the quark model, 0 minus plus and the 1 minus minus. If you keep going, you can get the 2 minus minus, the 3 minus minus, the 4 minus minus, the 2 minus plus, 4 minus plus. Okay, and then these were all the odd parity. And then you can also get these even parity states, the 1 plus minus, the 1 plus plus, the 2 plus plus, the 3 plus plus, 4 plus plus, 3 plus minus. But then you can also suspect there are other combinations that were not in this, they're actually not allowed. For example, the 0 plus minus is not allowed from this construction. Okay, you can't get 0 plus minus from these. You can't take L and S to get 0 plus minus. And then 1 minus plus and the 2 plus minus, these are what are called so-called exotic states. And so you can see what's predicted, right, and what's observed. And so these would be outside of the quark model, okay? And so these are some calculations that have been done to look for these exotic particles here, as well as to confirm these states that have the traditional quark model quantum numbers. But what's also interesting is that there's also a lot of interest in what's called the glue ball state. So here's a glue ball state, a 0 minus plus state. Okay, so expected that there might be a glue ball way out here, but it's unstable, it decays rather quickly. So that has not been observed experimentally. So here are some pictures of these various, here's a picture of a glue ball here. Okay, and you can also have various hybrid mesons, we've talked about them before, where we have a combination of this simple quark model picture with some gluons as well. And these are the so-called exotic states. Now, there has been a lot of interest in what are so-called pentaquark states. So a pentaquark state is one where the word is, the term pentaquark is actually a little bit misleading. It's actually 4 quarks and 1 antiquark. So you have something like this, quark, 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 like a baryon, and then you have a quark antiquark. Just for shorthand, they call it pentaquark, although it's 4 quarks and an antiquark. Now, back in the early 2000s, about 2003, there was a lot of excitement because they thought that there was something that looked like a pentaquark state, what was called the theta plus state, with a mass of maybe about 154 megaelectron volts over c squared. This was then other people, so this was seen in Japan at the time, but then other laboratories started looking for this. Some saw it, but then a bunch of them didn't see it, and then eventually it was realized that this was probably an artifact of some detector cuts that they were doing. Anyways, it was not confirmed. So the thought was that there was some like quark pentaquark state that could be here, something like maybe like a nucleon, or some baryon like a nucleon plus some meson that is bound together. So there was a lot of excitement, but that went away. Now, however, in 2015, when the Large Hadron Collider turned on, there was a collaboration called LHCb that looked at states with heavy quarks. And what they did was they found, first of all, this was not new, but they created what's called a lambda B0 baryon, which in the simplest quark model picture has a bottom and an up and a down quark. And so, but this decays through the weak interactions, and so this produces a W minus particle, right? And so then this then decays and forms an S quark and a anti-C quark, and you can also then have here a U bar and a D coming from the vacuum like this. Okay, and then this branch becomes a charmed quark, and this just remains an up quark, and this just remains a down quark. And so what they believe they observed, sorry, I meant to go all the way up here, this right here, was what's called a PC plus state, all right? And then this is just a regular old K minus state. So what this, the quantum numbers of this PC plus state is very similar to like a proton with a charmonium, if you like, okay? And so they observe these pentaquark states. However, it seems like these pentaquark states require having a heavier quark like a charmed quark. And so there's been a bunch of activities. They've observed other pentaquark states now as well. Now, let me just conclude with just a comment about this study of the hadron structure and then the relationship to looking at the structure of the nucleus. So in this hadron spectroscopy, they're looking at things like the origin of confinement, okay, the origins of mass and spin, and these quantum numbers and symmetries, what goes inside of the proton. But then there's also lots of calculations being done of the structure within the nucleus. Okay, what's the origin of the nuclear force, the origin of the binding and spin, and similarly the quantum numbers and symmetries that are allowed. So let me stop there. That's the completion of our discussion of quantum chromodynamics. Next time we will talk about quark gluon plasmas, which is also related to, obviously, quantum chromodynamics, but it's a separate topic we'll cover.